I emailed through with you guys yesterday, or this morning, I don't remember. What I'm looking at, ladies and gentlemen, we have a lot to go through, and I know you guys don't like to try to keep up sometimes. I got through all my material with plenty of time first hour. I expect to do the same 12th hour. Like I had said, we are probably just getting through the first 3 sections of Chapter 5, which is the first quadratic unit this week. Usually 5.2 is all the factoring stuff. This sometimes leads into a little bit of Wednesday, which isn't a big deal, because then on Wednesday into Thursday we can work with 5.3, and then on this day it's going to be the combination of all the word problems. I hold off on all the word problems until the end of these first 3 sections, because that's when I teach you how to use a calculator. Okay? There's going to be a time and a place for calculator usage, and when we do the quadratic word problem modeling stuff, that's the time and the place for the calculator. The rest of it, we don't need it. Okay? So, like I've done before with you guys, and I've told you that there are going to be calculator, non-calculator stuff. These first few things would be non-calculator. Then, obviously, on the word problems, you'll have a lot of crummy decimals and fractions and things. If you understand what values mean and what certain parts of quadratics mean, using the calculator to get to them is super easy. But we wait for crappy-looking problems to do that. We keep the normal stuff to start with. Right? Now, I know that all of you guys have graphed quadratics before. Do you remember what a quadratic looks like? What's that? A big formula. What is this? What's this called? It's a parabola. Just like the song. So the parabola is in. Right. It's either going to be up like a cup or down like a frown. Quadratics have different forms. Today we're going to talk about 3 of them. We're going to talk about standard form, vertex form, and intercept form. And when we graph them, each one of them, depending upon the way that it starts, is how you're going to work with it. And from what I've seen, one of these you've done, the other 2 are pretty easy. Okay? So quadratics are going to be written in the form of this: some function ax squared plus bx plus c. Okay? I'm pretty sure this would look somewhat familiar. Okay? So, yes. What's that? Oh, you know what I was doing earlier today? Here, watch this. I had everybody's like facing this whole row like this. Keep moving your seats. You're more able, you can see it better. I thought, yeah, I can do it. Does that help? See? Yeah, thank you. Help me out. So, what happens here with quadratics? Normally, what I always do is that I like to label everything, because if I know what my coefficients and everything are going to wind up being, I'm going to be better off. You might want to write this down and not sleep. Thanks. Trust me on this. And the reason that I do this is because if I know what my value of A is, I will always know what direction the parabola is. Right now, we only have parabolas that go up like a cup or down like a frown. Okay? For now. Later on, we'll have parabolas that go left and right, but those won't technically be functions because they don't pass that vertical line test. And we'll do that when we get to conics in a couple of weeks. So, grab a couple of sheets of this. We're going to do some examples, and I have some problems for you. We'll need 2. Yeah, I made the nice ones for you guys this time. Okay. What I want to do is look at that example we did on that pretest. I believe it was 3x squared equals negative 45 plus 24x. Does that sound about right? Yes. Okay. How'd that go? I believe that's what it was. We double check. Yeah, take 2. That's what it was. So this is what looks like in a what a quadratic will look like. Yes, sir. There's plenty around, guys. Pass them back. There's more back here on the chair. Just grab one and send it over. Remember, when you're working with quadratics, you want to get one side equal to 0. And in this problem here, I was asking that you guys solve the quadratic equation. Now, most of you guys set this one up to factor. And when you set things to factor, the first thing you always look for is what? The GCF, yeah, the greatest common factor. And I'd say about half of you guys got that far without too big of a deal. And you realize that everything here was divisible by 3. So you get x squared minus 8x plus 15 is 0. So you got to that. Now, in this case, what I would do, and I'm going to walk you through how we solved this and what it means after it's solved to look at its graph. Okay? Here, what you were doing is you were figuring out what times what is positive 15 that adds together to get negative 8. Yes, sir? Correct. Remember, two things that multiply together to be positive that add to be negative both have to be negative. So that means that your terms, things in parentheses, were x minus 5, x minus 3. Now, that's how it would be factored, but the question was to solve, which means when you have terms, you set them both equal to 0. And that gives you zeros at 5 and 3. So that's the way that you would have answered that question correctly. I'd say about half of you guys got that. Most of you guys that got it wrong wrote it as the answers were -5, -3, because you were thinking of, oh, in terms of -5, -3, you didn't take it that step back to what does that mean? You have to send it to 0 and so on. So using this equation here, this x squared minus 8x plus 15, I'm going to use that as what we call the standard form of an equation and take the parts out of it to show you what the graph looks like. So when we talk about standard form, that is the ax squared plus bx plus c. And we had f of x is x squared minus 8x plus 15. What's the difference between f of x and y equals? So is y equals. Yeah, they're just saying that's a function of x. It means the same thing. Textbook uses f of x a lot and also uses y equals. Just try to keep it reminded. Because a parabola is a function, because in a parabola, it will always pass that vertical line test. Vertical line will always touch it in one spot. Okay? That's what it means by it passes the vertical line test. So what we do with these, when we start looking at how to graph these, first thing I always would do is list my coefficients. What are the a, b's, and c's of that function? 1, -8, and 15. Okay. Now, a couple things you can get from that information right away. If I start thinking about it in terms of graphs, parabolas, remember the term symmetric? Parabolas are symmetric on themselves, which means one half of the parabola will fold into the other. You guys remember that? Which means that somewhere in the middle of a parabola, there's what we call an axis of symmetry. So what we do here, when we graph things in what's called standard form, the very first thing you always do is you list what is your axis of symmetry, your AOS. The axis of symmetry has a generic equation defined. And some of you guys started writing this down. The opposite of b over 2a. And that will be the x value. Because it's a vertical line, vertical lines are always x equals. Okay? Excuse me. So in this case here, if I take my coefficients that I just listed out, what's the opposite of -8? 8. It'd be 8 divided by 2 times 1 equals 4, which is my axis of symmetry. So what I've told people before, as we get into quadratics really become very procedural. And for most of you guys, once you see a procedure, you can replicate the procedure and you replicate it well. That's what quadratics do. Okay? There's not a lot of ambiguity and there's not a lot of waverness of, oh my lord, what do I set up to this? How do I do this graph? How do I do the constraints? I don't know what to do. It's fairly straightforward. If it's set up one way, you follow those rules. If it's set up another way, you follow those rules. Okay? So we have this what's called an axis of symmetry at x equals 4. So what I do is move Devin. Where if Devin bounces? No. What we do is we put a dotted line at x equals 4. Because is that line really there? No, it's not. Okay. But what will always lie on the axis of symmetry will always be the vertex of the parabola. So the vertex is always going to be some ordered pair x, y, but it just so happens that this value of x is always the coordinate of the x of the vertex. Yes, sir. What's that? When we have the axis of symmetry, it's a line that's there that isn't there. We use it to plot points off of because the vertex will go through that axis of symmetry, and each point if there's a point that's 2 spots away from it on one side, there has to be a symmetric twin 2 spots from the other side. We use it for like a counting spot. Okay. So if I know that my axis of symmetry is at 4, that means my vertex will have an x coordinate of 4, which means all I have to do to figure out what my y coordinate is take and substitute in f of 4. Oops. So I get 4 squared minus 8 times 4 plus 15. That's how I figure out where my vertex is. What's 4 squared? What's 8 times 4? 32. So 16 minus 32, negative 16. Negative 16 plus 15 is negative 1. So that tells me I have a vertex then at 4, negative 1. And I plot it. Okay. Now, I know that this graph had an a value of what? 1. So if my a value is 1, am I going to be up like a cup or down like a frown? Up like a cup. If your a values are positive, you're up like a cup. If your a values are negative, you are frown. So when you get to this point, always go back and look at your a value. If it's positive, you know you're moving up. If it's negative, you know you have to go down. So if and when you start substituting points in, if it's going the wrong direction, you know that you messed something up with the sign. Now, what you were asking earlier about why do I put in that axis of symmetry is because all I have to do now is pick a couple points on either side, and I know I can substitute in values. Okay? For example, if I pick the value of 3, I already know that we've done this problem a minute ago. If I substitute in 3 for x, 3 squared minus 8 times 3 plus 15, what am I going to get? Well, you get 0, right? Remember a couple minutes ago we factored it. We said that if when it's 3, it's going to give you a 0. That's where that came from. So 3 squared is 9. 9 plus 15 is 24. 24 minus 24 is 0. Yes, sir. Yes, sir. When you factor and find your zeros, you're in essence figuring out exactly where it crosses the x-axis. Sometimes it's integer value, sometimes it's not. Sometimes it's imaginary. Sometimes it's not there. So if it crosses the axis at 3, see how that's 1 spot off the side of the axis of symmetry? Which means its symmetric twin has to be 1 spot on the other, which was at 5. Okay, that's where we got that from. So I'm getting symmetric twins. So I know I have a set of ordered pairs at 3, 0, 5, 0. I just need one more set of twins. Pick the next number, 2. Can I pick 1? Can I pick -7? Does it matter? What's a really, really easy number to substitute in for x? 0. Because if it's 0, that becomes your y-intercept. What's your y-intercept of this function? 15. Everybody see that? If it's 0, it's 15, which means that I have another set up here at 0 and 15. And that's okay, that's off. It's not a big deal. You're just labeling it. And how far away is 0 from the axis of symmetry? It's 4 spots. It means I have to move to the right, to the right, whatever direction I was. How many over? Which makes it at 8. And there's your graph. You're using that axis of symmetry, the line that is there but really isn't there, to get points on either side of it that bounce on both sides. Okay? That's where that comes from. Yes, ma'am. You can pick whatever you want. Make numbers that are easy to work with. Whenever you're in standard form, one of the things that's kind of nice about standard form is that obviously your axis of symmetry is always going to be the opposite of b over 2a. Your y-intercept is always going to be at c, no matter what. It'll always be at your c value. Okay? Because if you substitute in 0 for x, 0 squared is always 0. If 0 times x will always be 0. 0 plus 0 is 0 minus 0 will always be 0, and that's where you get that from. So it's a nice thing to be able to remember because it's a quick point. So in essence, really all you have to do is just get one point. The other one's easy. Okay? Do we vaguely remember that? That's usually the most in-depth that you guys did with your regular old quadratic equation stack in Algebra 1. Okay? There's 2 other formats that we use for this that are both fairly simple because it's procedural. It tells you what things mean. You substitute, you pull those parts out, you plot them, and then you use that axis of symmetry again to plot points to bounce off on either side. Okay, so let me show you the other format. The other format is called vertex. What does that look like? Remember how we did the absolute value graphs with an h and a k? Where was that h and k for the absolute value? That was the vertex, the place to start, wasn't it? What did the a value tell you in the absolute value? Slope told you it was going up if a was positive, it was going down if a was negative. What do you think a does here? Same exact thing. A is positive, up like a cup. A is negative, down like a frown. H and K will be your vertex. Yeah, horizontal is moving from 0, horizontal, vertically. And where's the axis of symmetry going to be at? At when x is equal to h, because that's your vertex. Okay? This is a super easy one. If A is positive, up like a cup. A is negative, down like a frown. Vertex, located at HK. Axis of symmetry is at x equals h. When you graph via vertex form, it is so quick. Okay? The only thing that's not as super easy with vertex form is that getting that your y-intercept, you know how we said it was c in standard form? Getting your y-intercept out of this one takes a little bit longer, so this one you usually just find 2 points on either side of the left, either on the left or the right of the vertex. But those things are, the vertex and the axis of symmetry are super quick. Let me show you that. I know. What's that? It's not space here, it's a fan. Not me. I wrote y equals 2 times the quantity x plus 1 squared minus 4. Today we'll use some graph paper. When I'm starting these things out, I think it's easy to use the graph paper report. That way it helps you find the axis of symmetry. You can count your ordered pairs a little bit quicker without doing that. It's not like when we did your graphs on your own where you can scale it. These, they tend to fit within the 10 by 10. And on quizzes and tests, I generally make sure that they fit on there. The worst thing that can happen, you could get a half-z. You know, I'm not going to make you do anything crazy with it. And I have an example here in a little bit with a half-z. And you'll see, oh, it's not that bad. Again, the very first thing I'm going to do here is do my A, H, and K. Because that's the format that I did. What's my value of A? 2. Is it up like a cup or down like a frown? I'm going to do that right away. Okay? I'm going to do that right away because I know that it's positive. What's my H and my K? Good. H is -1, K is -4, which puts my vertex where? Oh. At -1 and -4. Where's my axis of symmetry? -1. Okay. From that information then, I can plot the axis of symmetry and my vertex and then pick really easy points to work with. Shall do this. See if this works. If I throw this on just one side, can you guys see that all right? Can I do it like that? Because if I put it on the yes or no, it's not. No, it's not, because it's x minus h. So if it's x minus h, x minus -1 is positive 1. Case is always the same. Case is always what it is. It follows the exact same rules. What's that? Yeah, so it means k is -4. Remember, when you're working with these, things, it's x minus h. So whatever the sign, whatever it is inside the parentheses, it's always the opposite. And then it's plus k, so it is whatever that value is. Because what's x minus a -1? Actually, let's do this. So I have an axis of symmetry at -1. And where was my vertex again? -4. Where's that next super easy point to work with? 0. Okay. What is 0 plus 1? 1. What's 1 squared? What's 1 times 2? What's 2 minus 4? There you go. So we're at 0 and -4. Did we say -4? Or did we -2? I'm sorry. Okay. What's that? We used 0 for x. We put 0 in for x. How many over to the right is 0 from the axis of symmetry? 1, which means how many to the left of it do I put a point? 1. So my other word pair is here at -2, -2. So we're at 0, -2, -2, -2. And then again, I go to the next point. Do I have to use -3 or should I use 1, which would be easier? 1. Okay. What's 1 plus 1? What's 2 squared? What's 4 times 2? What's 8 minus 4? 4. So my next ordered pair would be at 1, 4. 1, 4, which is 2 away from the axis of symmetry, which means at -3 will also be 4. And there's my curve. I'm getting pairs of symmetric twins via that axis of symmetry. See why we plot that? Because you only have to do half the work. That's the reason why it's there, but it's not there. Okay? Yes, ma'am?
So will it ever matter to use vertex and
You'll use whatever you're given.
Okay.
You know, you can manipulate the equations to go either way, but sometimes it's just not worth it.
Okay.
You know, you'll see stuff as we go along here. Like, on this first one, what would you use? On this one, what would you use? On this one, you would use what I'm going to show you here.
Okay.
Okay. So, like I was, yes, ma'am. Like I'm saying, like she was asking, when do you know when to use what? It depends upon what you're given. There's only 3 ways you can make it work, and I've shown you 2. And so far, nobody's like bleeding from the eyeballs, so that's a good sign. Devin, are you okay? Devin, are you dead? Are you bleeding from your eyeballs? Okay. Not quite dead. I haven't. No. All right, and the last form is this thing called intercept form. Intercept form is when you already have it factored. Intercept form is factored form. What's up? Double up. Blind squirrel finds an acorn. What we have here is when you have a quadratic that's in its terms. And now you're going to hear me say this a lot over the course of the next few weeks, and actually as we get into rationals and all that other stuff. As we get in further and further and further into algebra, basically the sole fundamental theorem of algebra, which is a thing, the degree of your polynomial tells you how many terms you should have. How many terms you have tells you how many zeros you should have. So if I have a quadratic, that means I have a second degree polynomial, which means I should have up to 2 terms. Terms are what things that go inside parentheses. Zeros are when you take these things in parentheses and set them equal to 0. So if you go back a minute ago, we had that x minus 5, x minus 3. We said that our zeros were 5 and 3, and that's where you cross the x-axis. The intercepts, like you were saying, Mr. Brown, a second ago, about the x-intercepts. That's where this comes from. We're going to graph it via, don't worry. This intercept form is graphing via the x-intercepts. Okay? So here's what happens. You still have the a value. That's going to be positive. It'll be up like a cup. The a value is negative. It'll be down like a frown. But more importantly, when you have your zeros, when you have your zeros, to go back to that original example, remember we had the one where it was 3 and 5? We said that those were the zeros. Are those 2 values on the same horizontal line? Which means those 2 values have to be symmetric twins. Which means the axis of symmetry always lies the midpoint of your zeros. No matter what ordered pairs you have, if it's a quadratic, remember we had 0 and 15, 8 and 15, where was the axis of symmetry? At 4. The midpoint of your symmetric twins always has the axis of symmetry. So no matter what, when you're in this intercept form, the axis of symmetry is going to be at the midpoint of your zeros. Okay? It'll always be, yes ma'am?
I don't think it wasn't it that
Oh. And to think that I even remembered them today. That's what I get for being proactive. Oh well. I know. I'm not quite dead yet. You're bleeding from the arms. You have no arms. Come here, I'm not here like we're just gonna leave. Peace out. Let's look at this one. Maybe. Let's look at this one. On this one, you are given your example in what's called intercept form. And you'll be able to tell which form it is because it's got two terms. If it's, yeah, I know, it's crazy, isn't it? If it's that term squared, that means it has to be vertex form. If it doesn't see any parentheses, it's the standard form. Where are your zeros located here? Careful. Your terms are 2 and -1, which means your zeros will be at -2. Remember, what we're doing here is that our A value is -1. Okay? Now, our zeros are going to be x plus 2 is 0, x minus 1 is 0, so we'll be at -2, positive 1. So if I plot that, I have -2, positive 1. What's the midpoint of -2 and positive 1? -1/2. Okay. So if my axis of symmetry is at -1/2, that means I have that dotted line that's not there, but it's there. Okay. Everybody all right with that? Okay. Symmetric twins then. What's really, really close to -1/2? 0. Actually, I'm sorry. Let's get our vertex first. A is -1. Is it up or down? Down. Down like a frown. Okay. So if my vertex is located at, or my axis of symmetry is at -1/2 for x, I just use that -1/2 to figure out the y value. So I use my substitution again. It's going to be -1 times -1/2 plus 2, -1/2 minus 1. I'm going to rewrite this then real quick, because this is like worst case scenario. They just have to use some pretty simple fractions here. What's -1/2 plus 2 in terms of a fraction? 1.5, otherwise known as 3/2. This, right here, right here. Remember, I'm just substituting in to get my y value like we did with standard, like we did with vertex. Take your axis of symmetry, throw it in, that'll give you your y value for your vertex. So then -1/2 minus 1 would be -3/2. Now I know that negative times a negative is positive. When you multiply fractions, remember you're multiplying straight across, numerator times numerator, denominator denominator. 3/2 times 3/2 will be 9/4. So my vertex will be located at, no, what's your axis of symmetry? -1/2 and 9/4. Now, 9/4 is a smidge more than what? 2. Can you just plot a point a smidge more than 2? That's all you gotta do. Smidge more than 2. Okay. So I can do that, and then I can use 0 if I want for my next point, or I can use 1. I'm sorry, we already did 1. We can use 2 if you want to see how far it drops down. It does not matter how you set it up. All you're doing is picketing? Yes, we're picketing. We're going to pick another value of x to generate the value of y. So I would use, well, do you want to use 0? All right. If I use 0, -1 times 0 plus 2 times 0 minus 1. That becomes negative 1 times 2 times negative 1, which is 2. So that ordered pair would be at 0, 2. Because it's the next closest. If my axis of symmetry is at negative half, I just use 0 because then that's half over. If I go half the other way, it would be at negative 1. Either one is fine. If you don't want to plot it that close, you don't have to. You could pick 5 if you wanted to. It don't matter. I just put it at 0 here, and then things is here. And now I have symmetric twins. So it would be at, we have 0, 2, negative 1, 2, and then we had our intercepts were at negative 1 and 0, and negative 2 and 0. And that's what that stuff looks like. Yeah, to start with, I'd like you to get your order pairs. We'll worry about what those mean later on, especially when we get closer to zeros. Zeros are going to be really important for a lot of this stuff, okay? Yes, sir. Axis of symmetry is your x value. Substitute that value of x to generate your y. When you have your axis of symmetry, it's always going to be x equals something. Your vertex is always going to be x, y. Well, whatever this value is, since the vertex has to lie on that imaginary dotted line, that will always be the x coordinate for the axis of symmetry. I'm sorry, for the vertex. The axis of symmetry's x equals something is always the x coordinate of the vertex, no matter what. It will always be like that. All right. Wrong button. Oh, I wish I had moved that 0 around. Oh, I'm sorry. I thought I put the problems on there. Let me write those out real quick. I have 3 of each type. I thought I wrote it in there already. I'm sorry. I swear I did. So I have 21 through. Oh, sorry. 20 through 22, 27 through 29. Actually, I'm sorry, it was 28 through 30. And then okay. I got 3 of each type, throw on some graphs and call it a day. We'll start factoring stuff tomorrow. Yes, sir. I will put it out. I'll put it on the calendar. I've got the PDF files already there. I just forgot to put the numbers on it. Okay. You guys keep them down. I got people coming in here next time after class. I don't know what I decided to do. You probably want the fancy nice stuff with the good numbers on it, huh? I have more of the nice stuff back here. Here you are, sir. No problem.